Last week we established why storage is the central challenge of the energy transition. The sun doesn't always shine, the wind doesn't always blow, and the grid has to balance supply and demand at every single moment. Today we're going to look at what we're actually doing about it. The technologies that exist right now for storing energy at grid scale, what they can do, what they can't, and what's coming that might change everything. Because here is the honest starting point. We do not yet have a fully proven, affordable, deployable solution for the long-duration seasonal storage that a grid running on 80 or 90% renewable energy actually needs. We have excellent short-duration storage, we have promising medium-duration options, and we have long-duration technologies that are moving from demonstration to early commercial deployment right now. Let's go through them. Lithium-ion batteries, the workhorse. Lithium-ion batteries are the technology that made electric vehicles viable, and the technology that is currently being deployed at grid scale faster than any other storage option. You know lithium-ion from your phone and laptop, though those use a cobalt-based chemistry optimized for compact energy density. At grid scale, the same fundamental lithium-ion family is used, just in different chemistries optimized for cost, safety, and longevity, rather than compact size. The advantages are real. They charge and discharge efficiently. They respond to grid signals in milliseconds, faster than any conventional power station can adjust its output. They're getting cheaper every year. Grid-scale lithium-ion installations are now cost-competitive with gas peaker plants for short-duration storage. But lithium-ion has a specific limitation that matters enormously at grid scale: duration. A typical grid-scale lithium-ion system is designed to discharge for 2 to 4 hours before it needs recharging. That's excellent for smoothing out the daily solar generation curve, storing surplus afternoon generation, and releasing it in the early evening peak. For that application it works brilliantly. The problem is that a grid running on high percentages of renewable energy doesn't just need a few hours of storage. It needs storage that can cover periods of days or weeks when generation is low across an entire region. A cold, still, cloudy week in January. No wind, limited daylight. Lithium-ion cannot solve that problem at any realistic cost. Now, within the lithium-ion family, one chemistry deserves specific mention. LFP, lithium iron phosphate. LFP batteries use lithium, iron and phosphate. No cobalt, no nickel, no manganese. This matters because the cobalt used in other lithium-ion chemistry, the kind in your phone and most electric vehicles, comes primarily from the Democratic Republic of Congo, often under mining conditions that raise serious ethical concerns, and from a supply chain that is geographically concentrated and politically fragile. LFP removes cobalt entirely. It's cheaper, it's safer, less prone to thermal runaway and fire. It lasts longer in terms of charge cycles. LFP has become the dominant EV battery chemistry globally, accounting for over 55% of EV batteries deployed worldwide in 2025 and over 80% in China. In the US, tariffs on Chinese batteries have kept LFP penetration below 2%, but that is changing. Tesla has begun LFP cell production at Gigafactory Nevada, currently for Megapack grid storage. A larger Michigan facility with LG Energy Solution is scheduled for 2027. Ford is building its own 35 gigawatt-hour LFP plant in Michigan. US tariffs exceeding 100% on Chinese battery imports have made domestic LFP manufacturing an economic necessity rather than a choice. The only technology with realistic potential to displace LFP is sodium-ion. China currently dominates LFP manufacturing, a supply chain consideration Western governments are thinking hard about, but the technology itself is genuinely better suited to grid storage than its alternatives. Sodium-ion batteries, the emerging challenger. Here is where it gets interesting. Lithium-ion batteries, including LFP, depend on lithium, and while lithium is more abundant than often claimed, it is geographically concentrated. Around 60% of the world's known lithium reserves sit in the so-called lithium triangle of Chile, Argentina, and Bolivia. A significant portion of global lithium processing happens in China. For countries trying to build energy independence, swapping dependence on Russian gas for dependence on Chilean lithium and Chinese processing is a concern worth taking seriously. Sodium-ion batteries replace lithium with sodium, and sodium is one of the most abundant elements on Earth. It's in seawater, it's in table salt, it is essentially everywhere, essentially unlimited in supply, at essentially zero geographic concentration risk. The implications for cost and supply chain resilience are significant. Sodium-ion batteries are already going into electric vehicles in China. BYD launched sodium-ion powered cars in 2024. At the grid scale, commercial deployment is expected to accelerate from 2027. The honest caveats are narrowing rapidly. Energy density, the amount of energy stored per kilogram, has historically been sodium-ion's main disadvantage versus lithium-ion. But the gap has not just closed, it has reversed at the mainstream level. Mainstream LFP batteries currently achieve around 160 watt-hours per kilogram. CATL's current Naxtra sodium-ion cells already achieve 175 watt-hours per kilogram, ahead of mainstream LFP, not behind it. The cutting edge of LFP is pushing toward 200 watt-hours per kilogram, and CATL's next-generation sodium-ion targets the same figure within 3 years. To be precise about that 200 watt-hours per kilogram target, it is a claim, not a shipped product. CATL announcements should always be treated with healthy skepticism until the product ships at scale. But the current position is already striking. The technology that was supposed to be the lower energy density compromise option has already overtaken mainstream LFP on that metric. Sodium-ion battery shipments reached 9 gigawatt-hours in 2025, up 150% from 2024. CATL has signed a 60 gigawatt-hour sodium-ion supply agreement, the largest ever placed. The question for B2B buyers in 2026 is no longer whether sodium-ion works. It is where it wins and where LFP still holds the advantage. The manufacturing scale is not yet anywhere near lithium-ion overall, but the direction of travel is unmistakable, and faster than almost anyone predicted 3 years ago. Pumped hydro, the proven giant before lithium-ion existed at grid scale, the world stored energy one way. You pumped water uphill when electricity was cheap and let it flow downhill through turbines when you needed power. Pumped hydro currently accounts for around 90% of all grid-scale energy storage globally. It has been doing this job for over a century. It is proven, reliable, efficient, round-trip efficiency of around 70 to 85%, and some pumped hydro installations have been operating for 50 or 60 years with no end in sight. The problem is geography. You need 2 reservoirs at different heights connected by tunnels and turbines. You need suitable geology. You need access to water. And you need to be willing to accept the environmental impact of large reservoirs on landscapes and ecosystems. Britain has some pumped hydro. Dynawig in Wales, known as the Electric Mountain, is one of the most impressive engineering achievements in the UK. But the geography limits how much more can realistically be built. The sites that work are mostly already used. Globally, pumped hydro will remain the backbone of long-duration storage for decades, but it cannot be the only solution because the geography simply doesn't exist everywhere it's needed. Liquid air energy storage, the Manchester surprise. This one is less well known and genuinely fascinating. The principle is elegantly simple. When you have surplus electricity on a windy night when generation exceeds demand, you use it to cool air to minus 196 degrees Celsius. At that temperature, air becomes liquid, shrinking to 1/700th of its original volume. You store that liquid air in insulated tanks. When you need electricity, you allow the liquid air to warm and expand back into gas, driving turbines to generate power. No exotic materials, no lithium, no cobalt, no hydrogen, just air, cold, and a turbine. The efficiency is around 50 to 60%, lower than lithium-ion batteries but improving with better heat recovery systems. The advantage over batteries is duration. Liquid air can be stored for days or weeks, not just hours. It provides not just energy storage but grid stability services, the synchronous inertia that grids need and that solar and wind don't provide. And here's the specifically interesting detail for a UK audience. The world's largest commercial-scale liquid air energy storage facility is currently being built in Carrington, Greater Manchester, by a British company, Highview Power, with £300 million of funding, including from the UK Infrastructure Bank and Centrica. The facility will store 300 megawatt hours, enough to power 480,000 homes. It is scheduled to be operational in late 2026. Two more facilities at Hunterston in Scotland and Killingholme in Lincolnshire are working through the regulatory process for a combined 3.2 gigawatt hours of additional storage. If approved and built, that would be genuinely significant at UK grid scale. Liquid air energy storage is not a fantasy. It is under construction in Manchester right now. Green hydrogen, the expensive dream, and then there is hydrogen, the technology that attracts the most political enthusiasm and the most marketing budget in the entire energy storage space. Hydrogen can be stored for months. It can be transported through pipelines. It can theoretically provide the seasonal storage that batteries and liquid air cannot at sufficient scale, and it produces no carbon dioxide when used, only water. So why is it not the obvious answer? The round-trip process of converting electricity to hydrogen and back loses a great deal of energy at every step. Electrolysis is around 70% efficient. Fuel cells converting hydrogen back to electricity are around 60% efficient. The round trip returns roughly 40% of what you put in. Compare that to lithium-ion at 85 to 90%, or pumped hydro at 70 to 85%. But efficiency alone isn't disqualifying if the cost is right. The deeper problems are manufacturing, transportation, and storage. Green hydrogen currently costs 3 to 5 times as much as hydrogen made from natural gas. Electrolyzer manufacturing capacity doesn't yet exist at the scale required. Hydrogen is the smallest molecule that exists. It leaks through materials that contain any other gas, embrittles metal pipelines over time, and requires either very high pressure vessels or cryogenic storage at -253 degrees Celsius to store in useful quantities. Transportation by pipeline requires significant modification of existing infrastructure. By truck or ship, it is energy intensive and costly. The full picture: expensive electricity, input, inefficient conversion, complex and costly electrolyzer manufacture, difficult transportation, expensive storage, and another efficiency loss converting back to electricity. Each step adds cost. Each step is a point of failure. Hydrogen is by far the least efficient and most complex way to store electricity. There are applications where it makes genuine sense: industrial high-temperature heat, shipping, aviation, steel production. But as bulk grid storage, the economics are very difficult to justify when batteries and pumped hydro already exist for that purpose. So what does the storage picture actually look like? Before summarizing, it's worth being precise about what short, medium, and long duration actually mean, because this is often misunderstood. The duration classification refers to how long a storage system can continuously supply power to the grid at full output before it's empty, not how long it can hold a charge without losing it. Lithium-ion and sodium-ion batteries actually have very low self-discharge rates. A fully charged battery sitting idle loses perhaps 1 to 2% of its charge per month. You could charge it on a windy Tuesday and the electricity would still be there on a still Sunday. The limitation is not the chemistry, it is the economics of scale. To store enough energy to cover a week of low renewable generation for a medium-sized city would require a battery installation so enormous, so many cells, so much land, so much capital, that it is currently economically prohibitive. The cost per unit of storage for lithium-ion is still too high for seasonal storage to make financial sense at grid scale. As costs fall, and they are falling rapidly, that horizon extends. Sodium-ion, with its lower material costs and lower self-discharge rate, may push the economic duration of battery storage further than lithium-ion alone, but we are not there yet. So the honest picture today: short to medium duration storage, hours to a few days under the right economic conditions. Lithium-ion batteries, increasingly LFP chemistry, with sodium-ion accelerating. For daily and short-term balancing, this part of the storage challenge is largely solved. The costs are falling, the technology works, and deployment is accelerating globally. Medium to longer duration storage, days to weeks, liquid air energy storage, flow batteries, and large-scale battery installations, as costs continue to fall. Early commercial deployment happening now, including in Manchester, costs still high but falling, This is the frontier of current deployment, seasonal storage, weeks and months, the genuinely unsolved economic problem. Pumped hydro where the geography works, hydrogen for specific hard-to-electrify applications, new technologies being developed. The honest answer is that we do not yet have a cost-effective, deployable solution for the seasonal storage challenge at the scale a fully renewable grid requires. That gap between the storage we have and the seasonal storage we need is where the real work of the energy transition must happen over the next decade. That's the honest picture, not panic, not false reassurance, just the engineering reality of where we are and what remains to be done. Next time, another piece of the puzzle. See you then. Hit like if this gave you something to think about. Subscribe for a new video every Thursday. See you next week.